Okay, welcome everybody. Glad you're here. We're going to give everybody a couple minutes to get in the door, get your seats, and get comfortable, and then we'll get rolling. Welcome everybody. Thank you for being here. All right. Although other folks are still probably going to show up, I want to start, respect everybody's time and give you plenty of time to hear from our guest speaker. I've looked at the presentation and I'm excited, so you should be also. Um, Thank you for being here. I am Dave Slime, Conservation Director for Wild Virginia, and I've got some of my colleagues here, Jessica Roberts, Kylie McClatchy, and Darby Dreer. We're going to try to make sure everything runs right here. And like I say, you get plenty of chance to hear from our speaker, Paul Angermeier. Just some ground rules. We are recording this. If you like, introduce yourself in chat. Tell us where you're coming from. During the program, give us your questions in the Q&A box, and we'll try to address as many as possible at the end of the program. And just be aware that you'll get a follow-up email with links to the program that you can share with everybody, and probably some additional information that you can access. Just to say that this is one of many programs that Wild Virginia has. We focus most strongly on habitat connectivity and water quality. What Paul is going to talk about tonight really intersects with a lot of the work we do in important ways. It's obvious that it intersects with water quality, but I want to give my colleague Jess a chance to say a little bit about the connectivity program and kind of how that relates to all this too.
Thank you. Hi, everyone. So I do the habitat connectivity section for Wild Virginia, like Dave said, and our program this year. So one of our big things that we try to help Virginia is to create more wildlife crossings, obviously to reduce wildlife vehicle conflict on roads, but also we want to increase aquatic connectivity as well for our aquatic organisms when applicable, and increase the flood resilience of our infrastructure. So a lot of my program deals with asking for legislation and support to when, for instance, you're redoing a bridge or you're redoing a culvert, that you make sure you consider aquatic connectivity and terrestrial connectivity and flood resilience. So if you'd like to learn more about my program, just shoot me an email, jessica@wildvirginia.org. Thank you.
Great. And the other thing you can do is follow all of our many other webinars, of which Jess has several exciting ones coming up. So just keep in touch. Now that we've got you, you'll get our information, but please feel free to share it with everybody you know, because we've got a lot of great stuff. So now I am going to turn it over to Paul Angermeier, who is a wealth of knowledge. I'll tell you again, I've looked at his presentation already, and I'm really excited because I've already seen things that I didn't know. And so Paul, if you would like to take it over here, go ahead and share your screen and tell all the people what you know.
Great, thanks, Dave, and thanks to everyone for joining us. I'm excited to tell you what I know and what I think I know and get your feedback on all that. Now, if I can figure out how to, there we are. So you can see me now, see your screen now, and hear me okay?
You're great.
All right. So I'm Paul Angermeier. I'm a professor in the Department of Fish and Wildlife Conservation at Virginia Tech. I've been in that post about 36 years, so kind of know my way around the department anyway. But I'm, let's see if we can get that to advance.
Sometimes if you just tap on it with the thing and then it'll advance for you. Or hit your side buttons.
Okay, why is it not doing that?
Oh,
there it goes. Okay. Before I get started, though, I do want to acknowledge that my experience and opportunity in Virginia lands and waters came at a cost to a great cost to Native peoples. And Virginia, of course, has a rich heritage of Native Americans from east to west, including the Powhatan and the Monacan, the Tutelo, or those groups that lived around Blacksburg, and then to the west, the Cherokee. And so it's important to recognize those folks as, I'm going ahead of myself, as we proceed. And many of those groups are still thriving. So it's not that they're simply in our history. All right. So what I want to do today are really develop broad brush answers to these two questions. How does climate change influence stream fishes, with a focus on Virginia, and which species are most vulnerable to climate change? And so to do that, I'm going to, in very broad strokes, outline a couple things. And I have 3 sections more or less in this talk. The first is a very brief primer on the ecology of freshwater Virginia fishes. Secondly, I want to talk about some of the key physical dimensions of climate change, in particular water temperature, stream flow, and fine sediment. And then the bulk of my presentation will talk about various aspects of the consequences for freshwater fishes of changes in climate change, changes in the climate. And to do that, I'm going to draw on some general knowledge, but in most of the time, I'll be drawing from case studies from my own work in my lab and collaborators. So this nice, colorful pie chart gives you a very quick overview of Virginia freshwater fishes, and it's a wonderful place to work on fishes. It's very diverse as states go. The bulk of the diversity is represented in the red and orange pie pieces by minnows, as also called cyprinids, and darters, which also called purses. So these are the main families in the Virginia fauna. But there are significant numbers of suckers and sunfishes and catfishes and sculpins. And there's a whole slew of families that have only a few species. So overall, there are over something like 200 and something, 200 and I don't know what the exact number is, over 200 native species and another 20 or so non-native species. So a very diverse system to work in. Now, rather than focus on particular species for the most part, for the context of this talk, I want to group them very broadly into these sort of temperature guilds or groups. And here I'm going to just lay out 4 groups: cold water, cool water, warm water, and combinations. And a good example of a cold water species is brook trout, one of many people's favorite fish. In terms of cool water species, candy darter is one that I'll talk a good bit more about later. For warm water species, it's typical of the sunfishes, for example, and most of the catfishes. Largemouth bass is a common example. And then there's a few species like American eel that are really tolerant of all sorts of temperature conditions. And so they don't fall into any particular category, but they sort of have a category of their own because of that breadth of tolerance. Now, another aspect of fish ecology that's important to outline here in the context of global climate change is where fish eat and what they eat. So most fishes eat things in the water column, but a very important group of them also feed on the bottom. These are called benthic fishes. Now, what do they eat? Well, fishes will basically eat anything that has any nutritional value, and that ranges from all sorts of plant material like detritus, algae, and macrophytes. Some fishes eat other vertebrates, but the primary group of food type that fishes eat are invertebrates, or small things like insects and mollusks and such that occur on the bottom of the stream. And those are the bottom feeders, and those that are specialized on vertebrates are especially vulnerable to climate change. And I'll talk more about that in a few minutes. So I just want to put some faces on the names of some of these benthic fishes because they are striking in their appearance and shape and so forth. And so here's a few of them just I threw up so you get a feel for what they look like, because you wouldn't necessarily know them if you didn't see the images of them. So on the upper right, I've got two species of darter. The top one is the candy darter, and the second one is the Roanoke log perch, and I'll talk in more detail about both of those later. And the bottom right, we have a couple minnow species, the sucker mouth minnow and the central stone roller. On the lower left, I have a couple sucker species, Roanoke log perch and the river red horse. And then in the middle, I've got a banded sculpin, and in the upper left is a mountain madtime. So a wide range of behaviors and shapes and sizes of all these benthic fishes. And the great majority of these are specialized on eating insects. All right, so another thing to focus on here is reproductive habits. And so in this case, you can group fish into several different groups. Where do they reproduce? What sort of substrate do they put their eggs on? And to what extent do they care for those eggs? So most fishes put their eggs on the bottom someplace, and those are again called benthic habits. But they're very particular about where they put those eggs. So some of them specialize on putting it on mud or macrophytes or in cavities, but the great majority put their eggs in some form of gravel or cobble. And there's a lot of variation in terms of how much energy they spend on taking care of those. And basically the way they take care of them is to clean or aerate those eggs in various nests or clusters or whatever. And so I very coarsely grouped fishes into those that provide some parental care and those that don't. And the ones that provide some parental care, particularly those that are in putting their eggs in gravel and cobble on the bottom, those are groups that are particularly vulnerable to changes in climate. All right, I want to introduce a concept here that's very important to maintain in the discussion about climate change, and that is the term regime. And I use regime commonly throughout my presentation here, and that's in contrast to sort of instantaneous condition. And that's because most of the important physical features of streams that control population and community dynamics of fishes are very temporally dynamic. And those include things like discharge, which is what fancy name for stream flow, and temperature, and the amount of sediment that's loaded and moved around in a stream. So all those are highly variable through time. And that variability, especially in the context of how it affects fishes, is at least as important ecologically as the average condition. So I'm going to talk about the regime of some of these features more than the average condition. And just to illustrate this, here's a hydrograph or a plot of changes in flow of the Powell River between January of 2010 and October of 2021. And just focus on the blue lines. That's the observed values. The orange values represent some modeling we tried to do to mimic the blue, but that's not really relevant in this particular context. But what you'll see here then is this wide range of sort of spikes and valleys. And in fact, the flow in terms of cubic meters per second in the Powell River ranges from somewhere around 50 to well over 700. So huge variation in how much water might be coming down that channel. Now, so it's better to think about in terms of characterizing flow regime in this case, in terms of the frequency, the magnitude, and duration and timing of those floods, not so much the average amount of water. And then also the rate of change in case, for example, if the spike suddenly goes up or if it's more of a gradual. So those kinds of features of frequency, magnitude, duration, and timing and rate of change are really important ecologically, and they have differential effects on things like survival and reproduction and growth and so forth. And those same kind of descriptors apply to temperature and sediment dynamics as well, but they're less commonly used in that context. So let's talk a little bit about some of the projected shifts in precipitation regime that we can expect over the next 60 to 70 years. And this is a graph I pulled off of NOAA's website, and it's really handy. You can go there and enter any locality, county, city, whatever, and it spits out this nice graph of a whole suite of precipitation metrics. I chose total precipitation, annual precipitation, just for convenience. And just to kind of walk through, it's a bit busy, but let me walk through what you're seeing here. So on the left, you see those bars that stick up and down. Those are measured values of precipitation in actual years. And then what the gray spiky web around those is the modeled, sort of the smoothing model that NOAA uses to say what that might look like if you could smooth across all those time frames. And then to the right side, you have projected precipitation based on what happened from 1950 to about 2010, looks like. And so two things emerge from this plot that are striking to me. And if you look on the far right, you see the numerical axis. 0 is basically the average. And so what you see is the average annual precipitation has kicked up starting probably about 2000 really, but in the last 10 years at least. And it goes up and then kind of levels off. So it's about 3 to 5, 6 inches above the period before, say, 2010. And I should point out, I just picked out, you can do this for any locality. I picked Richmond just arbitrarily, more or less, because of represent Virginia. The same sort of pattern would apply to almost anywhere. But what's most striking about this, aside from the uptick in average precipitation, is you get this huge change in variation. And so what this means going forward is you still see some of the low spike, the spikes pointing downward are going to be drought years, and the spikes pointing upward are going to be super wet years. And what you're seeing are super wet years like NOAA's flood coming periodically at far more frequencies than we've ever witnessed. So you see some of those really fearsome blue spikes going way up. I mean, those are hugely wet years. And we're still getting some drought years, but so the lows don't change so much as the highs do. Oh, and I should point out also, there's two sets of emission levels modeled here. One is the blue is for lower emissions, so less climate change, so to speak, and the peach color is for higher emissions. So anyway, you still see lots of variation in either of those. So what's that going to do to flow regime? Well, I didn't find any models of projecting actual flow regime changes, but you can kind of deduce what's going to happen. You're going to see greater average stream flows because that's going to reflect the increased precipitation. But what's really going to happen, important to fishes and everything else that lives in the streams, is more flashiness, greater temporal variation. And that's going to be associated especially exacerbated in urban areas, and especially pronounced in small streams. So more flash floods are going to be what we're going to see. All right, so we can do the same sort of projections for temperature regime. And again, NOAA has these handy plots that you can pull up for any locality. And in this case, you see a couple, the same sort of format, so I don't want to go through that again. But you see the same sort of pattern, but more striking because you see this inevitable uptick in average temperature that goes ever upward and significantly over what we've seen in the last even 20 years. And along with that, you get this tremendous variation. So you can see the band of the pink and the blue on the right side of the graph far exceeds the bands on the gray side. So what we're going to see are these, some years are just going to be horrific hot, and others that are going to be, they won't be horrific cold, but they're going to be cooler, but nothing like the cool that we've had in the past. So those days are gone. We're going to see we're going to be looking at much higher temperatures in our temperature regime, as well as this wild variation from year to year. All right, so what does this do in terms of sediment? I didn't find any projections of what's going to happen with sediment, but you can also kind of deduce what's going to happen based on the things that drive sediment transport and deposition. And that is particularly fine sediment loading into streams is driven primarily by intense precipitation, particularly rainfall. So the more rainstorms we get, we're going to get more fine sediment in the streams. And that has also important consequences for nutrient composition and transport, because that water coming off the hill slopes has stuff in it. And some of that stuff is phosphorus, for example. Most of the phosphorus that comes into streams is adhering to sediment particles. So it's locked into that anytime you have a runoff event. And there's also more nitrogen, not because the nitrogen is so much attached to the sediment, it actually tends to be dissolved. But what happens is, if you look at sort of watershed scale or landscape scale nitrogen budgets, a good bit of that nitrogen is deposited by wind to atmospheric deposition. So it ends up on the land and is periodically then flushed into the water whenever there's a runoff event. So a lot more nutrients going to be entering along with these rainstorms. All right, so let's shift and talk about what happens to the fish, everyone's favorite group. And I'll start simply with a species, or groups of species really, that are particularly sensitive because of their temperature tolerance. And I'm going to use brook trout here because it's a favorite of many folks. And it turns out that 20 years ago, Pat Fleavy was in our department, and she and colleagues published this interesting work, which is a little bit dated, but I think the message is still pretty clear. They projected habitat suitability, or the availability of suitable habitat for brook trout at a series of different increments of temperature increase. Again, within the range of what we can probably expect. And these are fairly simple models. And what you see clearly from upper left to lower right is this ever shrinking amount of suitable habitat for brook trout, to the point where when you get down to over 5-degree increase of current, you've lost 97% of suitable habitat. So that's a grim outlook for brook trout. And what you have along with that along the way is this increasing fragmentation of where they can persist, and the populations are getting increasingly isolated. And if they wink out, then there has to be an awful lot of management applied to get them to be put back in. And brook trout are really in a pickle here, because they're already relegated to the upper parts of mountains. So they don't really have any place to migrate to. They can't go to more suitable habitat. They're basically stuck, and their habitat is going to be increasingly shrinking as we go forward, even with not such egregious changes in temperature. What happened? There you go. All right. So let's talk about some species that are particularly sensitive to fine sediment. And here I'm going to talk about, in particular, Roanoke log perch and some of its associates. And this, for this set of slides, I'm going to draw from work that we recently, some colleagues and I recently published this year. And for those of you who don't know Roanoke log perch, they have a particular sensitivity to fine sediment because they have this peculiar habit, illustrated here on the lower left, of flipping small stones to get at the insects and so forth that live beneath those. And so if their substrate, if their stream bottom is filled with fine sediment, there's no stones to flip, and if they could flip them, there would be no bugs on them anyway. So they really take a hit when the fine sediment blankets their streams. All right, so just to sort of summarize the more general impacts of fine sediment, and just point out that this isn't simply a consequence of climate change. This has been going on for centuries. It's already a very pervasive, chronic, and strong effect on lots of fishes, invertebrates, and everything else that lives in streams. It's just going to increase with intensity, with storm intensity. The amount of fine sediments coming into these streams is going to increase. So that's the prognosis anyway. But fine sediment has profound effects on at all kinds of organizational levels in communities, from individuals to populations to communities. So it really impairs the breathing and eating and reproducing of lots of critters. It impairs habitat quality. It slows down or impairs production dynamics in general. And so the ultimate upshot of all that is that you have a lot of streams that are impaired simply because there's too much mud. Some species become imperiled because there's too much mud. And we're also, there's human outcomes that are undesirable in terms of loss of important services such as clean drinking water and recreational fishing. So increasing fine sediment is the big deal. Now, a couple ways that we measure that for those of you who are sedimentologists, one is called embeddedness and one's called silt cover. So this cartoon is a nice illustration of embeddedness. It just means the extent to which individual gravels or cobbles are filled or surrounded by very small particles like silt and sand. In contrast, the silt cover is the extent to which there's this fine blanket of fine sediment atop the stream bed. And both of those can have consequences for silt sensitive fishes and other critters. So in this analysis, we're not going to look so much at particular species, but look at species that share certain traits. And those traits are going to be, we chose those traits to reflect sensitivity to deposited fine sediment. And so in this case, again, we're looking at where the fish eat, what kind of food preferences they have, what kind of parental care they employ, and what kind of substrate they spawn on. So in this case, we're going to hypothesize that benthic fishes are more sensitive than water column fishes in terms of where they feed. And benthic specialist feeders are going to be more sensitive than generalist feeders, and those that provide parental care are more sensitive than those that don't. Lithophil here is just a fancy term for fish that love clean mineral substrates, so lithophil. So lithophils are those that really require fine gravel or clean gravels or cobbles, and non-lithophils are those that can get by without that. All right, so we conducted this study in the part of the upper Piedmont of Roanoke River, which is home to a lot of fishes, including Roanoke log perch, but there, in this particular area, there was over 80 species that might, in our samples, we actually caught over 40. So it's pretty diverse fish fauna. And we chose the sites here, it was illustrated in the black circles on the upper right, to reflect this really steep gradient in how much sedimentation was coming in there, because we wanted to be able to measure that effect on fish fauna. And so the way we did that is sort of illustrated in the lower left. We divided this landscape into small watersheds, and we used a modeling technique called revised universal soil loss equation to estimate how much sediment was probably coming into that based on things like land use and channel slope and cover soil erodibility and those kinds of things. That's a fairly standard way to do that. So collectively then, our 30 sites represents this gradient in how much sediment is probably entering these streams. And so we then now analyze the abundance of these various traits that I talked about earlier, and use that as a response variable in a number of regression analyses. And I'll just give you the upshot of what we found. It turns out that abundances of all those traits that we examined responded negatively to fine sediment. And embeddedness was especially impactful on feeding traits. Silt cover was especially impactful on spawning traits. The largest effect was the effect of embeddedness on those specialist feeders. The smallest effect, even though still significant, was the effect of silt cover on the lithophils, or those fishes that require clean substrates to spawn. Interestingly, we looked for but didn't see any threshold response. So in fact, there was more or less linear response, increasing decline in abundance of these traits across the whole range from 0 to 100% of these sediment metrics, which just says that no matter, just adding a little is still bad, adding a lot is even worse. And I won't show you here, but we also conducted some additional analyses on individual species to look at population responses, and those were essentially consistent with these trait-based analyses. So we feel pretty confident that we've got a pretty good, believable story there. Now I'm going to shift to another group of species, and of course some get double whammy because they're sensitive to temperature and sediment. And a good example of that is candy darter, which is endangered. And this grim map shown here illustrates why they're endangered in part. All the red dot lines are places that at one point in history had candy darter, but they've been extirpated. And you still see a few tiny little snippets of green down in Virginia. There are 4 populations left, all small, in Virginia of candy darter. So the bulk of what's left of candy darter range is still in West Virginia, but they're being threatened by an invasive species, variegated darter. So they're not necessarily any more secure than these tiny little snippets we see in Virginia. So anyway, it's in a bad place, but not so much because of climate change or even because of the more recent addition of variegated darter, but we think it's very sensitive to, and has been for decades, even centuries, sensitive to embeddedness and to temperature change, which has been occurring for decades. And so this is a bit hard to read. I pulled this this image from Corey Dunn's thesis, but let me kind of walk you through it. But just pay attention to the upper 2 plots. And these are plots of regression analyses showing responses along gradients in the x-axis to daily temperature, and on the right to embeddedness. And what you see then is, as you move from left to right, you see a declining probability of occurrence. And the other thing to note here is Corey went to a whole bunch of places, including all the places where candy darter had been detected historically, as well as a number of places where it looked like they might be there, but the habitat was suitable looking, but whether or not he actually found a few new ones, but a few new locations, but for the most part did not. But what he's shown here in this plot are the black dots are places that they were historically documented. And what you see then very clearly is and so if you have a black dot at the top, it means it was detected, and a black dot at the bottom means that they were not detected. And what you see then is this very distinct difference between where they were detected historically and now no longer detected in terms of temperature. So warmer temperatures, they're gone. Higher sediment, higher embeddedness, they're gone. So that gives us this circumstantial evidence that these are 2 factors that are really driving the outcome of that map I just showed you a minute ago. And this outcome is supported by other work that Corey did for his degree. And these plots represent probabilities of occurrence, basically habitat preference by adults, juveniles, and young of year along, again, gradients of embeddedness and silt cover. And in all cases, all age classes are much less common in places that have high embeddedness or in places that have high silt cover than the converse of that. So they're very particular about their sediment choices, and that the increasing sedimentation is exacerbated by the increasing temperature, which explains why they're so rare now. All right, I'm going to shift gears and talk about combined effects of urbanization and climate change. Of course, climate change doesn't occur in a vacuum. We've also got other things going on in the landscape that are maybe not so good for a lot of stream systems. And so this, I'm going to draw from work that I collaborated with some folks up in Maryland. This is 15 years old, but I think it's still germane to the conversation here because it does look specifically at some of the projections for climate and how it affects, in particular, stream fishes. So our goal here was to essentially predict the separate and combined effects of both urbanization and climate change, both of which are very large stressors on streams. And in particular, then we developed this forecasted indices for fish model, which I'll show you more of the guts of that later in a few minutes here. It's complicated. So I want to kind of walk you through the details of it. But that model is based on those traits related to fish growth and reproduction that we've already sort of alluded to. And then integrate this fish response model with other submodels that have already been developed by the same colleagues on hydrology, geomorphology, water temperature, and so forth. And then ultimately subject those to a whole series of climate scenarios and see what the responses of the fish are likely to be. Let me just walk through some more of the details here. And I already told you about those 4 groups of temperature tolerance fishes. This expands on the detail of that. And so what we see is 6 instead of 4. And the 6 are just combinations of cold and cool and cold and warm, because you've got fishes that can be put in those intermediate boxes. But the main point I want to point out here is that when you assign fish to say a cold or cool water box, it doesn't mean that suddenly when you go above some temperature, everything dies. What happens is you get this, instead of this sort of sudden mortality, you're more likely to have incremental changes in growth and survival, which ultimately means that that population might wink out. So it's not so much a instantaneous disappearance or loss of fish, but it's going to be over time, because again, the temperature regime is highly variable. Anyway, so we used those fishes from those 6 different groups, and then we also calculated these fitness measures, and these are related to reproduction and growth. And so the 4 metrics that we used were the annual availability of spawning days based on temperature and photo period that's suitable for each species, the substrate suitability based on how prevalent siltation was during the spawning season, juvenile growth, which is basically a function of water temperature, and adult growth, which is a function of water temperature as well as the availability of suitable foods. In this case, we looked at 4 food types: detritus, algae, invertebrates, and small fishes, and those are differentially important to different species. So this is a nice cartoon summary of the model, just to give you a sense for how the pieces fit together. So we've got on the very top, you've got these 2 major stressors or drivers of change: urbanization and climate change. Each of them differentially affects these intermediate stressors of sediment, flow, and temperature, and those interact then with food availability. And then collectively, those things all in various ways affect fishes through the effects on the availability of spawning substrate, adult growth, juvenile growth, and the availability of spawning days. So that's a complicated model that I won't go into any more detail than that. But we evaluated those responses at a daily time step, and I'll show you in very general terms what we found. But first, here's our baseline. So we looked at current conditions in several headwater perennial streams in the Maryland Piedmont, and those streams supported over almost 40 species of fish. And we're trying to look at the effects of urbanization here, but we're already choosing streams that have some degree of urbanization. So in this case, our set of streams is already subject to 10% impervious surface, which is fairly high. It's definitely urban. But those streams still had significant forest cover, 20%. The riparian buffers were still forested. And there was no, for the most part, no active construction or additional urbanization going on. So the baseline was this, and then we changed, in order to model the urbanization effect, we changed it out to this. So we jacked up the amount of impervious surface from 20% to 30%. We reduced the forest cover by 90%. We deforested the riparian buffers and began adding additional urbanization. So this is a fairly credible range of parameters to add to a watershed in Piedmont of Maryland. And so then with doing that, on top of that, we then added in these to get at these modeled climate change scenarios. We identified a number of projections, and we estimated those impacts of those projections at daily time steps over a 10-year period, quite far in the future, 2085 to 2094. And there are many forms of climate projections to draw from. And so we chose 4 that were sort of middle of the road, credible, and they vary in terms of what kind of atmospheric and oceanic circulation is invoked, as well as how much emissions are assumed. So we're going to use these 4 listed here, the Hadley, the parallel, and then there's the A2 and the B2 are different versions of those that represent different amounts of emissions. So just basically 4 different climate scenarios to model. And then our scenarios, we had 10 of those. So we had the baseline, we had the urbanization alone, and we had the 4 climate change ones alone, as well as the climate change plus urbanization combinations. So 10 different scenarios, and we can look at all those outputs. I'm not going to bore you with the details of that, just to give you a sense for the range of analysis that we were trying to do with this. And this is just an example of some of the output. So in this case, we're just looking at projected water temperature during the summer of the year 2090. And what you see here is the lower dashed line is basically the baseline scenario. And then all the other scenarios are, you show an uptick in water temperature. And so in both the urbanization only and the climate change only, you see a significant uptick above baseline. But then those effects are additive. So if you look at climate change plus urbanization, you get an even bigger uptick. And so that just tells you that there's this synergistic effect going on, at least with temperature. And when you add climate change on top of urbanization, it's already probably going on. All right, so we found lots of variation in the outputs of our various scenarios, and I won't try to go through the details of that, but just to give you some very general patterns. The life stages of fishes that were affected in each scenario vary considerably across species and across scenarios. So it wasn't any one simple outcome for those. You had to kind of look at them collectively to get a sense for what's going to happen. In fact, few species showed similar simultaneous effects in terms of juvenile and adult growth. What you had was some of the scenarios were predominantly affecting the adult growth, others were predominantly affecting the juvenile growth. But what we did see, though, is that when you combine urbanization and climate change, you typically saw an increased number of species with impaired adult growth. So that was if you expect climate change and urbanization to really occur together, it's the impaired adult growth that looked like to be the most impacted. So our overall patterns are shown here. It turns out that from what we can tell, widely accepted climate models are predicting pretty severe, extensive ecological impacts on, at least through the lens of stream fishes. And those effects of urbanization and climate change are additive or even synergistic, say multiplicative. Anywhere from half to 3/4 of stream fishes in those systems will be stressed under some combination of urbanization and climate change, and including game fish species. So a lot of those are likely to decline in abundance just because of the stresses on growth and reproduction. And finally, although we didn't see lethal temperature thresholds crossed very often, it's those sublethal effects, the incremental effects on growth and survival and reproduction that are really driving the bus on these kinds of impacts. All right, my next little chapter here is on invasions of introduced fishes. And you may not think of introduced fishes as being a problem with connected to the climate change, but I think it is, and I'll try to make that case here. But first, let me just, in broad strokes, point out the problem with introduced fishes in general. It's already a major threat to a lot of native fish assemblages. It tends to, or the introductions that we're seeing are compromising a variety of ecosystem functions and even human economies, and costing in some places millions of dollars a year. The number of introductions is increasing rapidly. either through accidental or intentional pathways. And one of those pathways, or a series of pathways that I want to focus on today, are international trade. And international trade is a key catalyst for a number of introductions, particularly the aquarium trade, the live food trade, and the water garden trade. Now, what I'm showing here on the bottom are two very impactful introduced species. In the middle there is northern snakehead, which is introduced from Eurasia. It's wreaking havoc in parts of Chesapeake Bay. And another species on the lower right is blue catfish, which is introduced from other parts, is native to the Mississippi Basin in the central U.S., but it's been introduced into Virginia sometime in the 1970s, and it's really wreaking havoc on a lot of the Chesapeake Bay fauna, including oysters and blue crab and a whole bunch of other fishes and mussels. So it's, as you can tell, both of these species are predators, so they eat a lot of stuff. And although the blue catfish wasn't introduced because of the three pathways I've shown here, aquarium, live food, or water grading, it was introduced to enhance recreational fishery, which it has done, but at a cost. All right, so I'm going to give you really quick background on a project that I'm involved in now with a number of collaborators. We have a paper in review, and the gist of it is that we're trying to predict the invasiveness of a whole suite of freshwater fishes that are imported in North America. We're doing that in the context of 4 different regions that we think represents a good bit of the U.S. and Canada. The Sacramento, San Joaquin over in the west, Lower Colorado, the Great Lakes, and of course the Mid-Atlantic, which includes Virginia and Maryland. Our findings are kind of listed here in very simple terms. Some of the most common predictors of having invading fish established are the climate match between the source region and the recipient region. And that makes sense because if your climate doesn't match, you're not going to do very well. And also the species temperature tolerance. So both, and we've talked about temperature tolerances already, will vary widely across species. But this is this next item is probably a little more striking. There's a huge variation in the number of species that are traded that might be predicted to establish. In the Sacramento, San Joaquin, there's over 500 that we identified. Not so much in the Mid-Atlantic, only about 5, and that largely reflects the differential attributes in terms of climate and temperature and so forth. The most common source continent is Asia, for collectively across those regions. Let me just introduce this concept too, and I'll show you in a minute why. There's a concept widely used among ecologists called ecoregion, and that's basically just a way to divide the world into sort of homogeneous regions that represent similar relationships among organisms and their environment. So these regions are often delineated based on things like precipitation, temperature, landform, and soils. And what you get from this is a spatially hierarchical stratification of all the environmental conditions in the world, and you put those into these sort of spatial polygons. And within each of those polygons, then you can assume that those water bodies are experiencing somewhat similar environmental conditions, and they're clustered in space, and they're more similar to each other than outside of the ecoregion. And I bring this up because a recent paper that just came out this year looks at projected effects of fish invasion in the context of climate change. And this is a bit busy figure, but let me kind of walk you through. So what these folks did was they looked at 426 freshwater ecoregions, 821 terrestrial ecoregions, and they compared the matches of region to region, pairwise regions, pairwise matches of regions, and plotted the difference. On the left-hand side, you see a particular future climate scenario, whereas on the x-axis you have the historical climate scenario. And the diagonal red line is basically a one-to-one relationship. And any of the regions plotted above the line means that there's greater climate match. Those plotted below the line means less climate match. This is between pairs of regions. So the upshot of this is that as we move forward into, if this particular climate scenario is anything representative of the future, what you're going to see is increasing numbers of ecoregions that are welcoming to more and more species that are traded and introduced globally. And so we're going to see a lot more places that will be suitable for introduced species than we have seen in the past. All right, so in conclusion then, here's some sort of very simple, maybe pithy summary statements. In a projected future for our stream systems, I think the evidence is that we're going to see higher temperatures, higher flows. This is all very on average, higher sediment loads, but much more temporal variation, more imperiled species, and more non-native species. So some of those I would find undesirable, and some of you may agree or not. So with that, I will open it up to questions and comments.
That's amazing, Paul. I think we can probably all agree that it's discouraging to see a lot of these things. I think one of the things that we try to stress is that we can't get immobilized by the scope of some of these big problems. One of the things that I'd like you to maybe talk a little bit about, you talk about the value of headwaters, small streams. And I guess the fact that they can be really sensitive because impacts can be exerted by not that huge of an activity. But maybe the other side of that is that we have the chance to kind of preserve some of those places by not doing necessarily such drastic things. Does that make sense? Can you kind of talk about that a little bit?
That's right. Yeah, and in fact, if you were going to invest in any kind of restorative actions, I mean, that would be the smart money would be to do it on small streams, because there you have the capacity to actually see the impact. And the closer you are in terms of watershed and or riparian and or other kinds of activities, it's going to show up in that small stream far easier than in a much larger, or a river. You know, a river is going to integrate everything upstream of it. And so in order to do anything significant, everything upstream of it, that's going to be a tremendous challenge. Whereas with small streams, you can figure it, and it's been demonstrated, I think, that's where the action needs to be. And even if you wanted to approach restoring the conditions in a larger water body, you have to start at the smaller scale watersheds anyway, and it's cumulative.
Yeah. There's another question I'll get to, but one of the things I'll point out to people is that a lot of times here in Virginia, especially, people talk about the Chesapeake Bay, they talk about the James River, they talk about the larger streams, but the outsized impacts of a little bitty stream as part of that system, pretty amazing, the role that they play. Somebody asked here, how good are the models that predict the effect of climate change? That's kind of a big question.
Well, I like to say that, and I'm paraphrasing, some smart person said, all models are wrong, some of them are useful. And so I think that's a good way to treat models. And so, I'm not going to hang my head on any particular model, but I think the value of the models comes in if there are lots of models that say the same thing based on different kinds of assumptions and so forth, then it's pretty good evidence that there's something going on there. And so, yeah, we can't, and that's why I showed those projections for temperature and precip for Richmond. They have wide confidence intervals in those, and that's they purposefully show those wide bars because no one can predict with much precision what's going to happen. But the trends are the takeaway there, I think, and the trends in the upward trends in temperature and flow are rain, and the upper striking upper trends in the variation. I think those are, you can take those home. That's going to happen. If you get down to
And-
the particulars of what's going to happen in a particular year, I think that's out the window.
Sure. Well, I guess one thing to know, I mean, you've been in this business a long time. I have too. And we can kind of check those models as we go through time. Can you say anything about what was predicted 10 or 20 years ago and what you've seen and how it reflects that?
Well, I'm not a modeler, so I don't
Sure.
dwell on those things so much, but I do know people who do invest a lot in modeling, and clearly they're always looking to improve the output and the predictive reliability of models. So I think you have to kind of look at whose model is it, and do they have an agenda, or are they being straightforward and objective? And so
Yeah.
this is always a struggle with any kind of scientific pursuit. Is we're all, the scientists are only people, and so they're subject to biases and so forth. And so there's a certain amount of self-correcting that goes on in the scientific process. And so, yeah, if a model that came out 20 years ago turns out to be bogus, someone's going to point that out. And so
Yeah.
that becomes no longer the standing the state of knowledge. So it is dynamic, but I guess I trust in the process of scientific pursuits, because it's fundamentally about disproving somebody else's stuff. So there's a lot of work that goes on, a lot of critical work that goes on to develop those models.
Okay, looking at some other questions here. In light of the current definition of waters of the US, what can we do to preserve pocket water? Of course, waters of the US, that's a legal construct under the Clean Water Act. Just quickly, the Supreme Court has kind of narrowed the authority of the federal government on the range of waters that it can protect. But do you want to say anything about that?
That's probably outside my bailiwick. I think you're probably far more. I mean, I appreciate the fact that the Clean Water Act has been reined in, and particularly for ephemeral or disconnected wetlands and such. And that, I mean, that's just one of these things I shake my head at. But
Yeah.
the same thing applies to the connections between surface water and groundwater. I mean, to an
Yeah.
ecologist, you really have to ask, what are you thinking? I mean, that doesn't make any sense. So the legality of it is kind of beyond my expertise, but the only, if not the Clean Water Act, sometimes there might be levers to pull if, for example, there are endangered species involved. It
Mhm.
wouldn't be presumably limited by that kind of perspective. So if it was shown to be that a particular wetland or disconnected water body was important to the persistence of endangered fish or mussel or salamander, I would think that you could work with that. But
Right.
in a general sense, it's just it's unfortunate.
Yeah. Well, I will tell folks, since I do look at the legal side, here in Virginia, at least, we're lucky because our state law essentially allows protection of every bit of water. It is not narrow like that definition. So take heart from that. And it's one thing we can be happy about. We're almost to time, but I'm going to try to get in all these. Do you know if anyone is looking at the changes in thermal impact of NPDES permitted discharges on smaller streams in the face of climate change?
No, I don't. Again,
Okay.
that's kind of outside I don't deal with regulatory issues much, other than maybe endangered fish, but.
Well, and there again, not to interject too much, but we are, while Virginia has been looking at that in relation specifically to construction sites, because we believe that some of those are probably contributing to higher temperatures. Here's something, practical steps for helping identify and reducing invasive species. So I guess, do you have any practical recommendations?
Well, the main recommendation generically is prevention is far preferred over trying to eradicate. Once the fishes are invaded, it's except for a few really isolated cases in some lakes and wetlands and things, it's impossible to extract them. So we have to do more to be proactive about keeping the things out in the first place, and state agencies and federal agencies as well are doing what they can to do that. But
Yeah.
it's a struggle because you can imagine there's a lot of economic forces against restraining, introducing species of all sorts, whether it's fish or horticultural species or whatever. So I mean, given the amount of trade and the amount of money that is involved, it's a huge struggle to control that.
Yeah. Well, we are at 7:31. I just want to read this last note that somebody said. Great presentation, which I will absolutely amplify. Thanks so much for this. Don't give up the fight to preserve our native species. I know you won't, and we won't either. So folks, you will get that follow-up email. You'll have this recording available. I think we can probably make the presentation itself available if that's okay with you, Paul.
Yeah, I'm good with that.
And again, thanks everybody. Keep following us and keep in the fight. So thanks so much.
You're welcome. Thank you.
And thanks folks for being here. Really appreciate it. All right. Well, that was great. That was great. A lot to think of it. Man,